On a whiteboard, theoretical physics is flawless, but the moment a physical copper wire hits the terminal, that mathematical perfection vanishes. Equations like Ohm's law are built for a frictionless universe. They assume wires have absolute zero resistance, and power sources deliver limitless, stable energy. Down on the engineering bench, physical reality asserts itself. Material constraints mean the pristine calculations written in a notebook will rarely align perfectly with the reading on a digital multimeter. There is a distinct observer effect in electronics. The very act of probing a circuit to measure its behavior inherently alters how that circuit functions. This split-screen comparison shows a standard voltage divider. On the left, our theoretical calculation yields exactly 7.50 volts. But on the right, the physical breadboard setup returns a reading of 7.52 volts. Mastering diagnostic analysis means treating the math as a baseline, not a guarantee. You have to anticipate the inherent physical flaws baked into both the circuit components and the measurement tools themselves. The first variable disrupting our math is manufacturing tolerance. The standard E12 series of resistors ships with a built-in error margin of plus or minus 5% straight from the factory. If we test a nominally rated 1 kiloohm resistor on the bench, it physically measures at 0.979 kiloohms. Before we even apply power to the circuit, we already have a 2.13% deviation from the theoretical model. Then we add the uncertainty of the testing equipment. Even high-end calibrated digital multimeters carry a baseline 1% margin of error in their DC voltage readings. But the most disruptive physical variable occurs when we try to measure current, a phenomenon known as ammeter burden. Look at this current divider circuit. To measure the current flowing through a specific branch, an ammeter must be placed directly in series with the flow. To take the reading, the meter introduces its own internal resistance into the path. This physical obstruction actually chokes the target current down from the mathematically expected 3.33 milliamps to 3.29 milliamps. Measuring voltage requires the exact opposite approach. A voltmeter connects in parallel across the component, requiring extremely high input impedance to ensure it doesn't create a secondary path that drains voltage away from the target. Physical circuit analysis is an exercise in damage control. It requires using mathematical compensation to account for these parasitic meter effects and material imperfections. These individual component errors compound rapidly when we evaluate complex DC networks, where multiple interdependent loops interact simultaneously to share currents and voltages. On paper, Parchoff's laws dictate perfect balance. The algebraic sum of voltage drops around any closed loop must equal zero, and the sum of currents entering a junction must exactly match the currents leaving it. Executing those loops on a physical breadboard fractures that perfect balance. Every single wire jumper, component leg, and metal node introduces microscopic contact resistance. Look at this 5-resistor bridge network. A slight degradation in contact resistance at a single physical node creates a ripple effect across the entire board, shifting the millivolt readings in low-current branches and skewing the entire system. If your goal is to predict how a specific load will behave when attached to this network, tracking these cumulative micro-errors across every single resistor becomes a diagnostic nightmare. This physical complexity demands a method of mathematical simplification. Engineers need a way to collapse the entire messy, error-prone network into a single, predictable black box. This is the exact function of Thevenin's theorem. It proves that absolutely any linear DC network, no matter how complex, can be mathematically crushed down into one single voltage source and one single series resistor. This relates directly to Norton's theorem, which achieves the identical simplification by substituting a current source and a parallel resistor. To build the Thevenin equivalent, we remove the load and measure open circuit voltage across the bare terminals, returning exactly 10.72 volts. Next, shorting those exact terminals together captures a short circuit current of 3.61 milliamps. Dividing 10.72 volts by 3.61 milliamps isolates the hidden Thevenin resistance at 2.97 kiloohms, collapsing the network. We test this simplified model by connecting a physical 1 kiloohm load resistor back into the actual circuit to see if our math correctly predicts the real-world current. The Thevenin model predicted a load current of 2.70 milliamps. Down on the bench, the physical circuit measured 2.44 milliamps, yielding a deviation of 9.6%. A 9.6% margin of error does not mean the theorem failed. It proves the theorem successfully condensed the cumulative impact of resistor tolerances and contact resistance into a single, functional power model. Moving away from the steady, one-way push of DC voltage, we enter the dynamic, oscillating environment of alternating current. In an oscillating circuit, the physics of the environment shift. At high frequencies, components offer reactance, a time-dependent opposition to the continuous changes in current flow. An inductor is simply a coil of wire, but its physical geometry gives it a unique trait. It actively fights any change in current by generating a reverse voltage, known as back EMF. Because an oscilloscope can only measure voltage, capturing this reaction requires a specific bench technique. We insert a non-inductive shunt resistor into the circuit, allowing us to safely and accurately visualize the current waveform on the screen. This oscilloscope display shows the physical evidence of the inductor's reaction. The yellow wave represents voltage, and the cyan wave represents current. Because the inductor resists the change in flow, the current waveform physically trails behind the voltage waveform in time. Here, we see a precise delay of 134.4 microseconds. We define this horizontal time delay mathematically as the circuit's phase angle. In this specific bench test, the inductor dragged the current so far behind the voltage that it created a phase shift of 48.4 degrees. In AC systems, time itself becomes a measurable physical dimension, dictating exactly how and when power is delivered to a reactive load. The ultimate physical variable in an AC circuit sits at the geometric center of the inductor coil itself, the core material. We can observe this by comparing the electrical properties of an empty air core coil against that same coil when a ferrite rod is inserted. The baseline bench data shows the hollow air core coil generates an inductance of 326.3 microhenries. Simply sliding a ferrite rod into the exact same copper wrappings causes the inductance to balloon to 955.7 microhenries, an increase of nearly 200%. This physical insertion also pushes the phase angle lag even further, shifting it from 70 degrees up to nearly 81 degrees. The mechanics of this shift are governed by magnetic reluctance, which operates as the magnetic equivalent of electrical resistance. This equation demonstrates the relationship between inductance, turns of wire, and reluctance. Ferrite possesses vastly higher magnetic permeability than air, providing a highly conductive superhighway for magnetic flux. Introducing the ferrite instantly shrinks the circuit's reluctance, causing the inductance to scale upward in inverse proportion. Mastering circuit analysis requires a kind of dual vision. An engineer must be able to calculate pristine, idealized mathematics on paper, while simultaneously anticipating the resistant, reactive, and magnetic reality of the physical materials on the bench.